All right, going to worksheet A for chapter 14. Going to be looking at numbers 1 to 12. So starting off with differentiating with our trig functions. So as we look at something like this, a couple important things to remember on these is one is as far as the rules for differentiating is you have those in your formula packet. So when I'm looking for the derivative of cosine, if I don't remember what that is, you can always go to your formula packet. Right here it tells us the derivative of cosine is negative sine. So when we go to set this one up, so starting off, it just starts out with a 3 times, so I'm going to say 3 times. So again, I know the derivative of cosine of 2x would just be the negative sine of 2x. So it starts off like this, but here's the kind of the main thing a lot of people forget, kind of like chain rule. You also have to multiply by the derivative of the interior function. So the interior function here is 2x. The derivative of that is 2. So that's something I have to take into account. When I do this, that's probably the biggest mistake made within this whole chapter. There are those people just who forget to include that as they go to solve, and they leave this as their answer, forgetting the extra 2. So if I combine the 3, the negative 1, and the 2, I get a negative 6 out front, and then I have my sine of 2x to follow. So moving on to number 2, 3 cosine of x squared. Pretty much the same idea. If you had a hard time with the first one, this is a great time to just kind of pause the video and try number 2, because it's a lot like the first one. So again, I have a 3 times to start things off. Again, we just saw that the derivative of cosine is negative sine, so I got to throw that in. So I got the negative sine of x squared. And this is where you have to recognize that the x squared is your interior function. So if I take the derivative of this interior function, the derivative of x squared would be 2x to the first. So I have to remember to include that and put that in. Without that guy, we're not going to get correct answers here. So if I combine what I have left here, so the 3, the negative 1, and the 2x gives me a negative 6x out front. And then I got the sine x squared to follow. Moving on to number 3. So now we're doing a similar idea, but now we're going from sine instead of cosine. So again, you need to know what the derivative of sine is. It's in your formula packet just in case, but derivative of sine is cosine. One thing to keep in mind with a notation like this is sine squared of x. That is the same thing as me writing it like this. The sine of x squared. And so you have the exact same thing. If it helps to write it that way, then that's a good way to write it. So going from here, one thing to recognize on this is we are simply doing the chain rule again. I have a function within a function here. So how do we normally approach the chain rule? We start with the exterior function. We take the exponent, we multiply it to the front. It's going to give me an 8 out there. Keep the interior function alone for a minute. Right? We subtract 1 from the exponent, so that now goes down to a first power. And then the next step in that chain rule is to now go into the interior function and do the derivative of that. So we know the derivative of sine is cosine. So I am multiplying by the derivative of the interior function, which is what chain rule is. And now if I just kind of, not much to simplify on this, it looks like I can get rid of the 1, but we can just leave it as 8 sine x cosine x for our answer. So always clean up as much as you can, try to make it look as simple as possible. Going on to the next one, number 4, we have another rule applying here for anything involving that base of e. He has a simple rule. The derivative of e to the x is e to the x, so that's not going to change anything when we go to write that, but one thing you just have to recognize on these is that interior function. This isn't e to the x, right? It's e to the cosine of x. We have an interior function going on here, so when I go to take my derivative, again, I got the 6 out front. The derivative of e to anything is that value, so derivative of e to the cosine x is e to the cosine x. But as always with chain rule, I now need to multiply by the derivative of the interior function. And the derivative of cosine of x, as we saw earlier, is negative sine of x. So I have to bring that into play. Otherwise, we're missing a big part of that answer. Simplify a little bit. I could take that negative and combine it with the 6. So I would just write that as negative 6 e to the cosine x sine x. So do simplify as much as you can. Moving on down, number 5. So find an equation of the tangent to the curve with the equation of y equals 1/2 sine x at the point with an x coordinate of negative 2 pi. So we are looking for the equation of a line, which keep in mind, kind of the main thing that we're looking for there is like a point slope equation. So that should be the first thing that comes to mind is needing to get the equation of a line. This is always going to be a good place to start. And they tell us that it is tangent to this curve right here. Remember, tangent just means it hits that curve in a single point. So whenever we're looking at this, two things we always consider. One is, what is the slope of that line? And the other one is, what is the point of tangency? What is that one point where this line hits that curve? And so that's where the x1 and y1 come in, as they represent that point of tangency. So one thing they gave us to start with is the x coordinate. So we already know negative 2 pi is the x coordinate. So we need to use him to come up with a slope and to come up with a y coordinate. So let me just start with the easier one first. How do we ever get a y coordinate from an x coordinate? Well, you just plug it into the original function. So if I take my negative 2 pi and plug it in right there, that will help me get the y coordinate. And so if we just consider what is the value of the y coordinate at negative 2 pi, and this is where it helps to have working knowledge of your unit circle. So remember, negative 2 pi is once around the circle in this direction. So if I go negative 2 pi, it's going to put me right back to where I started right there, which is at the point 1, 0. The sign always refers to the y coordinate, so we can see that it is 0 at that point. So the sign of negative 2 pi is 0. 0 times 1/2 is still 0. So I'm getting a y coordinate of 0, which will be really easy to plug that in for this. So we already have that part right there. Let me just write what we have so far. So we have our x1 and y1 that was already given to us. I just need to come up with a slope now to plug into that equation. And the slope you can always expect to come from the derivative. So anytime you plug in an x value into the derivative, you get a slope. So just like we did up above, I need to find the derivative of my function. So from y equals 1/2 sine x, doing what we did up above, the derivative of that, we keep the 1/2 out front, just like we did in the first 4 examples. The derivative of the sine of something, we know that derivative of sine is cosine. So I have the cosine of x. And so as you're looking at this function, there's kind of nice, there's no interior function right here that's just x, and the derivative of x is 1, so that's not going to affect us any further. So no interior function to worry about on this one, so we have our derivative. And now, as always, if I plug my x value into the derivative, I get my slope. So if I plug my negative 2 pi into that, I can get a slope from this. We already saw up here that negative 2 pi would put you at that point. The cosine refers to the x coordinate, which is a 1. So the cosine of negative 2 pi is 1. 1 times 1/2 is 1/2. So there we go with our slope. I can now plug that in. And now just a little cleanup. And I can get the proper equation of that line. Got the double negative right there. Obviously y minus 0 is y. And if I distribute the 1/2, I can write that as 1/2 x plus pi. Something you really have to keep in mind and read carefully with problems like this. This one just said find the equation, so we're okay with that as an answer. But there are a lot of times where directions will ask you for a specific format of your answer, and it's really important that you write your answer exactly in that form when the directions say that. So if it says, you know, in the form of, and it might say something like this. It might say something like ax plus by either plus c, or they can put c on the other side. They can do it either way. However it's asked of you, that's the way you need to write it. They can even say, make sure that your values for a, b, and c are elements of the rational number system or of the integer system. So it could say that they're rational answers, which means you can leave them as fractions. If it says they're elements of the integer system, then you need to write them as integers without fractions. So just to give you an example, in a case like this, if these directions followed, that a, b, and c had to be elements of the integer system, and maybe it needs to even be in that form, I would have to rework a couple things. For one, I could multiply the whole equation by 2 in order to clear my fractions, which would look like this. And if it asked me to put things in that form right there, I would have to subtract my x over to the left and write it like this. If they had the c on this side, I would have to subtract 2 pi over and put it on the other side, make the whole thing equal 0. So just really important that you follow directions for how they want you to write your answer. And of course, if we wanted to, I could multiply the whole equation by negative 1, so that my leading term is positive. But you don't have to do that. That would just be another way of writing the same answer. Either answer would be accepted. Moving on to number 6. So find by differentiating the gradient of the curve. Remember, gradient just means slope. So they're giving us a curve right here. Real similar problem to number 5. Only it's like one step easier because all I have to find is the slope. Instead of the full equation of the line like I did on the last one. I only need the slope. So remember how we got the slope on the last one. You find the derivative of this function, plug in a value for x, and the result is going to be your slope. Anytime you plug in an x into the original function, you get a y coordinate. Anytime you plug it into a derivative, you get a slope. So first things first, got to find the derivative. So if we look at the derivative rule for natural logs, so remember for this, if needed, you do have that shown to you in the formula booklet. So the derivative of the natural log of anything is simply 1 over that value. And so if we apply that to this one right here, let me just write this one down. So the derivative of the natural log of the cosine of x would simply be 1 over the cosine of x. One thing you got to consider on this is we have a function within a function. So here's the chain rule coming into play. I now need to multiply by the derivative of this interior function. So what's the derivative of the cosine of x? And we know it's the negative sine of x. And so I'm multiplying by the derivative of that interior function. Obviously I can combine that with the 1 on top and just call it negative sine x over cosine x. And so now if I go back to this, I have my derivative. I can plug x into these guys in order to get my slope. And so again, this is where you need a little working knowledge of your unit circle. If you don't have it memorized, there's something you can always go back to that will help you. If I multiply this by 180 over pi, I can convert that into degrees. If I multiply that by 180 over pi, I would see that that represents 30 degrees. So if needed, and I'd rather you not go this route, I would like you to at least have quadrant 1 memorized on the unit circle, but if you don't, here's kind of a fallback method. Remember, this all goes back to right triangles. So we're looking right now at a 30, 60, 90. Pattern for that we know is 1, 2, rad 3. And how do you ever find the sine or cosine of an angle in a 30, 60, 90? Sine we know is opposite over hypotenuse. So I know that's going to come out to be 1/2 at this point. Sorry, I kind of crammed that in there. Let me write so this point that we're referring to is this guy right here. So we just figured out that the sine, or the y-coordinate, is 1 over 2. Cosine does adjacent over hypotenuse, so rad 3 over 2. So voila, that's where that point comes from on the unit circle. So you can always kind of go back to that method in case you forget what those values are. It's just use a basic right triangle. So the negative sine of 30 degrees, or pi over 6, same thing. Sine is the y value, so that comes out to be 1/2. So I have negative 1/2 on top. The cosine is the x-coordinate, so I got the rad 3 over 2. If I multiply by the reciprocal of my fraction, so if I multiply the top times 2 over rad 3 and clean that up, I'm going to get negative 1 over rad 3. And typically we don't leave radicals on bottom, so I do this in order to what they call rationalize the denominator, or simply rewrite it so that there's no more radical on bottom, but this is the result that we're coming out with for that. And this is something you got to keep in mind with everything that I've done so far. The answers that we're getting are not decimals, right? They're coming out to be radicals. They're coming out to be trig functions. You're not going to get answers like that from a calculator. So even though there's some nice things that calculators help us with in this area, they don't give you answers like this. And so it's important that you can have the knowledge enough to come up with answers like this without a calculator, because that's what you're going to be asked to come up with. So moving on, number 7. So now we're moving into the opposite idea, which is now integrals. So these are the ones where you are starting with a derivative and you are finding the original function. So we're going back the other way with these. That's why you always have the dx attached to this, is because this represents the derivative function, and we are working our way back up to the original function. And so this one is a definite integral. They want us to integrate from 0 to 2 pi. So we're going to have a few numbers to plug in at the end of this. Anyway, if we're just going to start with integrating, whenever you have two separate terms like this, separated by a minus sign, just do each one separately. So the integral of x just becomes x2 over 2. The integral of cosine, so remember the derivative of sine is cosine, which means the integral of cosine is sine. We go back the other way, and so that's where we get the sine of x. You always have the formula packet for that in case you need to draw back on that. So we have our integral function. So this was the original function. That must have been the derivative of this for that to work out. And so as we're here, we can now plug in 2 pi for the x's and get a value. I can plug in a 0 for my x's and get a second value, and then we subtract those at the end. So if I plugged in my 2 pi right here, 2 pi squared would be 4 pi squared over 2. Which obviously I could reduce right here to just be 2 pi squared. So we're going to do that anyway, so let me just write it down. If I plugged in my 2 pi right here, so the sine of 2 pi, remember as we talked about earlier, 2 pi puts you at this value right here, which is 1, 0. So the sine is the y-coordinate, which is 0. So minus 0 is just that value. So 2 pi squared is the result from plugging in him. If I plug in a 0, obviously this term becomes 0, but the negative sine of 0. So at 0 degrees, which is also 2 pi, same thing, I'm in the same point. But the sine of this guy again is 0, so my answer just comes out to be 0 again. So this guy is all I'm going to be left with, because when I plug in the 0, I get a 0 for this, I get a 0 for this, so he has no value. So I'm going to be subtracting 0, which is still going to leave me with my answer of 2 pi squared. Going over to number 8. So number 8, same thing. We have our just another definite integral. Remember, indefinite integrals is when there is nothing here or here, and we got to make sure we put a plus c on our answer. But these guys actually have some values to plug in. So as we integrate the sine of 4x, so the integral of sine we know is negative cosine. You can get that from your formula packet if you needed to. So I got the negative cosine of 4x. Anytime you integrate, you have to remember to divide by the derivative of the interior function. So remember, when you're doing derivatives, you multiply by the derivative of the interior function. But when you're doing integrals, we divide by the derivative of this guy. So if I divide by the derivative of 4x, that's just dividing by 4. Or you could say I'm multiplying by 1/4. Same thing. So here is our integral function. We now move from left to right, so I'm going to need to plug in negative pi eighths and pi and subtract the difference on that. So let me start at the top and plug in a pi. So if I was looking at 4 pi, I'm still on the same point, because remember, when you go once around, you're at 2 pi, go again, you're at 4 pi, so I'm still at the same point right here. So the cosine of 4 pi is 1. This guy is going to make it negative 1 times this is negative 1/4. So when I plugged in pi, this should be the result from doing that. Now I need to plug in a negative pi eighths into this. Notice this says an exact value, so even though I could do this in a calculator and get a decimal, it may not give me an exact value if I'm getting decimals or an irrational answer, so you're going to need to know how to do some of this stuff without the calculator. But I'll show you kind of how you could plug this into a calculator if you wanted to in just a second here. Anyway, if I plugged in my negative pi eighths into this right here, let me write this off to the side. So negative cosine 4 times negative pi eighths times 1/4. So as I plug in this value, a little cleanup on this, and I'm going to get negative pi over 2. So if you kind of consider your unit circle, positive pi over 2 puts you at would put you at 90 degrees. All right, this is pi over 2 right here. So negative pi over 2 would put you right here at 270. These coordinates right here, I'm going over 0 and down 1. So I'm at that point right there. The cosine of that, remember, cosine is your x. In this case, that x is 0, so negative 0 is still 0, and 0 times 1/4 is 0. So even though whatever I get from this, I'm supposed to now subtract from what I got from this guy, but again, it's just another minus 0. It's not going to change anything, so I'm just going to be left with that negative 1/4 as my answer. So that's still an answer I could get in a calculator, because even if I do this and get a decimal, it's still going to be exact. So let me just show you in case you aren't familiar with how to do these. So under math, go down to the one that says function integral. So I'm going to that one right there, and you just plug in the stuff. So I can plug in negative pi over 8. So negative pi over 8 for that guy. If you go up to the top, I'm plugging in pi. Right here, I need to plug in the function of the sine 4x. Keep in mind, if I'm doing this in terms of pi, I'm going to probably need to change that to radians. We'll see how that works out and see if that matters on this, but I'm going to put in sine 4x. Sine 4x dx. Let me go into my mode really quick and change to radians. Get back to this. So that was our function. So if I hit enter, voila, there's our negative 1/4. Obviously it's in a decimal instead of a fraction, but this just said an exact answer. That's an exact answer. It's not rounded, so that would be acceptable. If you wanted a fraction, just hit math, fraction, enter, and we can write it as a fraction as well. So that's one that could have been done in a calculator, but they can't all do that. Sometimes you end up with stuff like pi in your answer, and you're not going to get that from a calculator, so always good to know how to do both. Moving on. So going on down to number 9. So we got a curve with this equation. They tell us the derivative of the equation. They give us a specific point. This is an x, this would be a y value. Find the original function, so obviously we need to integrate this in order to take it from being a derivative up to the original function. So that's what we're doing. So we're gonna integrate this guy. So we got the 4 out front, just keep him out there for a minute. We know the integral of cosine is sine, so I'm looking at the sine of 2x. Always when we are doing integrals, we then divide by the derivative of the interior function, which is our 2x right there. So you have to divide by the derivative of that, which would just be 2. So as I divide that whole thing by 2, obviously that would just become 2 sine 2x. So you got to notice for this one that this is not a definite integral, right? Definite integrals give you values to plug in. Indefinite integrals always come with a plus c because we don't know what that constant is. So we're dealing with a function that's looking like this at this point, but we don't want that plus c. We want a value there, so that's where this information comes into play. So this means if I plug in a 3 pi over 4 for x, I can set the whole thing equal to 1 and that way solve for c. So a little substitution here. So replacing the x with 3 pi over 4. So a little cleanup right here. If we reduce, that becomes 3 pi over 2. So think about where that would be on our unit circle. So 3 pi over 2 puts you right down here at 1.5 pi. So coordinates on that guy would be 0, -1, and we want the sign on that. So sign is your y coordinate, which is -1. So I'm looking at 2 times -1, which is -2, plus c. Add the 2 over. We got our value for c, and now we can plug that back in right back to this guy to finish it off and have our answer. So we would just write it as 2 sine 2x plus 3 as our answer. Without that information right there, that would have been my answer, but since they gave me this, I can go farther and solve for c. So moving on, number 10. So diagram shows part of a curve. So we got a cosine minus sine function. Find the sum of the areas. Area under the curve always means integral. So do keep in mind on this, anything above this axis is always going to show up as a positive, and anything below that axis is going to show up as a negative. But when it comes in terms of areas, areas are always positive, so I need to make sure I do these separately, turn this into a positive before I add it to him. So keep that in mind, but going down the list here, so if we integrate our function on this, so integral of cosine is sine, and integral of sine would be negative cosine. So we got that double negative right there. So just sine plus cosine is our I didn't mean to put derivative on that. So we integrated this to become this. So there's the function, and now I want to take the integral and first evaluate it from 0 to pi over 4. So here's where it's going to always help to, again, kind of have some knowledge of quadrant 1 of that unit circle. So pi over 4 is going to be this guy. Do keep in mind that if you ever don't remember those things, remember I showed earlier how you can use right triangles to create them. So just in case, if you were to convert pi fourths into degrees, so if I multiply that by 180 over pi, that would tell you that this is 45 degrees. So the pattern in a 45-45-90 is 1, 1 rad 2. And so if we did something like sine, I would get 1 over rad 2, which if I rationalize the denominator comes out to look like this. If I did cosine, it would be also 1 over rad 2, which would also come out looking like this. So those things can come from a right triangle if you ever get stuck on that, but that's an option. So anyway, the sine plus the cosine, they're both the same in this case. So if I just add those together, they would just add up to rad 2. So that's from plugging in him. Well, let me just write that down. So I'm integrating from here to here, so now if I plug in the 0, the sine of 0 plus the cosine of 0, those guys just add up to 1. So that represents this area of the curve right here. So keep that aside for a minute. I now need to find the area of this guy right here. So I have the same integral, but now I need to evaluate it from here to here. So slide that up a little bit. So now I'm doing sine plus cosine from pi fourths to pi halves. So if we plug those in, if we plugged in our pi over 2, that would be this guy right here. So for this coordinate, we're up here at 0, 1. So if I add those together, sine plus cosine, those add up to 1. And then I need to subtract whatever I get out of this guy. And we already know what that looks like from doing this one earlier. If I plug in my pi fourths, we know that already comes out to be rad 2 from what we already talked about. So I'm doing this result minus this result, which is what that would look like. So these are the two areas. Notice that would come out to be a negative. The square root of 2 is bigger than 1, so that would come out to be a negative. So I need to make sure that I take an absolute value on that. So just to show you what's going to happen here is basically those guys are going to change places. And here's how that would work. Notice if I did 1 minus the square root of 2, I get the negative answer, but if I flip them around, there we go. I'm getting the same value, but it's the positive answer. So I'm going to write it as rad 2 minus 1 so that I get the positive version of that. So there's my two areas. They were both the same value. So I just need to now add those two things together to get my total area under the curve. So rad 2 plus rad 2 is 2 rad 2. And if I had a negative 1 with another negative 1, I got my negative 2. So that would be the total area under the curve. Moving on to number 11. So again, we've got another function right here. We've got a curve. Find the area of the shaded region. It's the exact same thing. This one's a little simpler because it's just one area instead of two different areas that we have to consider. But notice the one thing they didn't tell us is our kind of our points here that we need to work with within that function. So we're going to need to plug in a couple numbers here so we can figure those out. Notice that the point I'm looking for right now, obviously that is at 0. So the point I'm looking for to go with it is on the x-axis, which means it has a y value of 0. So if I set this equal to 0, I should be able to solve for that value. So that's what we're doing here. So looking at that, if I divide the 6, it still equals 0. So we're looking at this and saying the cosine of what angle would give me a value of 0. So again, think back to that unit circle. Where are the cosines 0? The cosines are your x coordinate. So right up here at pi over 2 and down here at 3 pi over 2 are the two places where your x coordinates are 0. So I got two results for this. If you're looking at the graph, this is the one that we would have to be using because as this graph would continue, right, it's going to hit the graph right here at pi over 2. If the graph continued, it would come back up here and hit the line again at 3 pi over 2. But we're not going that far. So we're only going as far as the first intercept or the smallest intercept, which is pi over 2. So I know that the cosine of pi over 2 is equal to 0, which means pi over 2 must equal my x over 3. So if I multiply the 3 over to the left, then 3 pi over 2 becomes our x value. So that's what we just figured out for that value right there. So moving on. So I am I need to take the integral of this, and now I can evaluate it from 0 to 3 pi over 2. So if we integrate this, the integral of cosine we know is sine. So 6 sine of x over 3. Always need to divide by the derivative of the interior function whenever you're doing integrals. So the derivative of this would be 1/3. So I am dividing by 1/3, which is the same as multiplying by 3. So now I can combine those and get the 18 sine of x over 3. And we are evaluating that from 3 pi over 2 to 0. So if I plug in my 3 pi over 2, right here for x, that's going to become 3 pi over 6, which becomes pi over 2 after we reduce. So right here, we're back up here at pi over 2. Remember, the value for that is at 0, 1. So the sine of what angle, or sorry, the sine of what value is at pi over 2? Sine is the y coordinate, so we know it's at 1. Sorry, let me slide that up. So we know it's at 1. So the sine of pi over 2 is 1 times 18 is 18. So that's what we got by plugging in him. I now need to plug in a 0. So 0 divided by 3 is obviously 0. What is the sine of 0? So remember, at this point right here, this is at 0 degrees. The sine at that point is 0. So 0 times 18 is still 18. So that's all I got left. So when I plugged him in, I got the 18. When I plugged him in, I got 0. So obviously when I subtract, I'm left with just 18 on that. All right, last one, number 12. So giving us a sine function, they're not telling us what the a value is. They're just telling us that it's an element of the natural number system, meaning it's got to be a positive integer for that to be true. So first of all, find the value of a. Right, remember, a has to do with the amplitude of the graph, so it must be the 8 that we see sitting there. So that would be our value for a. So now we can obviously sub in an 8 right there and continue to work with the problem. So we're going to see this as 8 sine x as the function. So area of the shaded region, again, we're just doing another integral, and we're going to evaluate it from 0 to pi thirds. So if we were to integrate and we're going to evaluate that from 0 to pi thirds. So there's our setup right there. So if we do the integral, integral of sine is negative cosine. So I'm looking at negative 8 cosine x. And we're evaluating that from 0 to pi thirds. So when I plug in the pi thirds for cosine, bump this down a little bit. So it would be nice if you already knew the cosine of pi thirds. That's something you should know. Be familiar with the first quadrant. Let's just say you forgot or weren't sure. If I multiply that by 180 over pi, that tells me that's at 60 degrees. So if I build a quick right triangle for 60 degrees, I know the pattern is 1, 2, rad 3. So the cosine is adjacent over hypotenuse, so I know the answer to that is 1/2. So when I plug this in, I get 1/2. 1/2 times negative 8 is negative 4. So now I need to plug in a 0 and then do my subtraction. Do keep in mind that we can't come up with a negative, and through our subtraction, if we do this right, we should be okay. So if I plug in the 0 for cosine at 0, right, we already know the x coordinate of that is 1. So 1 times negative 8 is negative 8. So a little cleanup on that, and I can see my solution is 4. You know, with a case like this is one where, you know, obviously we came out with a perfect value like this natural number. So that's one that could have been done on a calculator as well that would have given us an exact answer like this one. So as I showed earlier in the video, you do have a function for that in the calculator. So you know, even if it's just a way of checking an answer, that's always a good thing to do. So if I go to math, go down to number 9, which says function integral, it gives me that setup. I could certainly plug in my values from 0 to pi over 3. Right here I got the function, which is 8 sine x, and then dx. If I just hit enter, oh, I'm in degrees right now, that's why I'm getting a weird answer. If I change my mode into radians, then we got our answer.